Alright, welcome to lesson 12. This is going to be the last lesson with new material for this unit. We're going to be talking about secant, tangent, and normal lines of a curve. So 3 different ways to talk about the equation of a line with respect to a curve that we're talking about. These are fundamental to understanding motion and are used all the time in calculus and in physics. And we'll find that with our new definition of instantaneous rate of change, or the slope of a curve at a given point, and using the limit to find that, is going to make our ability to create these lines a lot easier than might be expected without them. So let's go ahead and get started. Okay, so I have a little question for you, and what it's going to do is going to help you understand and discover what a secant, a tangent, and a normal line are. We're just not going to give them names quite yet. So we've seen this situation before. The distance away from the origin of a particle moving in a straight line is given by the function d of t, where d is equal to t squared. T is measured in seconds and d is measured in feet. And what your goal is to find the equations of each line that I've drawn here and describe what each means with regard to the motion of the particle. So let me just kind of direct you in what we've got going on here. Here is the function d of t. It's this quadratic function here. And I'll go ahead and label it d of t. Okay. And of course, the y-axis represents the distance in feet, and the x-axis t in seconds. Okay, so there are 3 lines that I've created here. The first is this red line. This red line passes through and intersects the function d at 2 seconds and at 8 seconds. Then there's this green line here, which not just intersects it touches the function d at 4 seconds in, but as you can see, matches up perfectly with it at 4 seconds in. So I'll let you think about what that means. And then this purple line is at a 90-degree angle to this green line here. Okay, so the last thing that you might want to review is point-slope form for a line. And that's the equation that we developed actually in the first video this summer to write the equation of a line if you know the slope and a point at which the line passes through. So go ahead and review that, and then find the equation for these 3 lines, and then we'll talk about which one is the secant, which one is the tangent, and which one is the normal. You can go ahead and take a guess if you'd like. Okay, if you got stuck or if you struggled to find point-slope form in your notes, I'm putting it up here now. So the way it works is if you know a point that the line goes through with an x value of x sub 1 and a y value of y sub 1, and you find the slope m, then the equation of the line is y minus whatever the y value of that point is, equals the slope times x minus whatever the x value of that point is. Okay? So if that was was holding you back, go ahead and pause again and finish out this question, and if not, let's go ahead and talk about them. Let's start with the first line. And you'll notice that this first line is exactly the average rate of change, the line with the slope that is the average rate of change between the points at 2 and the point at 8. So a point that it passes through, we have 2 of them already, so we could just use this first one. And then we just need to know the slope, and the slope is, of course, the change in y divided by the change in x. So our slope here for this line is going to be the change in y, which is 64 minus 4, divided by the change in x, which is 6, and that's equal to, of course, 10. Okay. And then a point that it goes through, we can choose either one. I'll use this one here. So the y value of that point is 4, the x value of that point is 2, and so the equation for our line is going to be y minus 4 equals 10 times x minus 2. Okay, And we can write this in a form that will maybe lend itself more easily to using it by solving for y. And so what we could do is we could multiply 10 times x, 10 times negative 2, and then add 4 to each side. And what that will give us is y is equal to, and so 10 times x is going to be 10x. And then 10 times negative 2 is negative 20, but I'll be adding 4 to both sides, so it's going to be negative 16. Okay? That is y-intercept form. Okay? So that's the equation for the red line. Now let's go ahead and take a look at the green line. Okay, so for the green line, we want to write the equation, meaning we need a point and we need the slope. Well, let's take care of the point first. So notice that this green line intersects our function d of t right at 4. Okay, so that's a point that they have in common, and so that's a point that's on the green line. So at 4, well, what is this point here? Well, that's the point 4, comma, now what's 4 squared? Well, that's 16. So 4 comma 16. So we have a point, and now what we need is the slope of this line. Well, notice that this line here matches up perfectly with our function d of t. And so if it matches up perfectly right at 4, then it's got to have the same slope as our function d of t does right at 4. In other words, we need to find the instantaneous rate of change, or the slope at this point, for our function d of t. And so there we can use the limit definition. And so the slope of our green line here is just going to be the limit as h approaches 0 of d, and this is at 4, right? So 4 plus h minus d of 4 divided by h. Okay? And so we can go ahead and find this value here. So we have the limit as h approaches 0. Now d of 4 plus h, that's going to be 4 plus h squared. And d of 4 is 16 divided by h. By this point, you know that if we plug 0 in for h, if we use substitution, we're going to get 0 over 0. So we need some algebraic manipulation. And to do that, we're going to need to cancel an h somewhere in the numerator and denominator. So we can go ahead and square out 4 plus h squared. That's going to give us the limit. Remember to keep writing your limit statements. The limit, and in the numerator we're going to have 16 plus 8h plus h squared minus 16 divided by h. And here I'm just going to go ahead and note that we have 16 minus 16, which is 0. And I'm going to rewrite 8h plus h by factoring out an h, since that's what we wanted to begin with. So it's going to be h times 8 plus h. And there we can now cancel. So I just have the limit as h approaches 0 of 8 plus h. Substitute in, and we get that this is equal to 8. So that is our slope. Remember when we wrote this as m equals? Right, this is the slope of the line, the slope of the curve d of t at 4 seconds, right? So we can think of this as being also the slope of the line that passes right alongside the function d of t at point 4. Okay? So the slope of our green line is going to be 8. And so now I can write my equation here. I'm going to use the point that it goes through, so it's going to be y, I'll write it right here, y minus 16 is equal to, the slope is 8, 8 times x minus 4. Alright, we can do the same thing where we put this now in slope-intercept form by multiplying 8 times x and negative 4 and adding 16 to both sides. And that will give me y is equal to 8 times x is 8x. 8 times negative 4 is going to be negative 32. But remember, we're going to add 16 to both sides, so that's going to give me negative 16 or minus 16. And so the equation of my line is y equals 8x minus 16. All right, last one is the purple line. All right. Now, looking at the purple line, we actually have all the information we already need. Just one part of it might be a little disguised. So the first is, what is a point that the purple line goes through? Well, we know that it crosses the function d of t at 4, and so the purple line goes through the point 4, 16. So we've got that taken care of. What about the slope? Well, notice that this purple line is perpendicular to this green line here. Now, if you've forgotten what you learned this summer, which would be shocking and amazingly ridiculous since it was only a few short months away, go back and take a look. When we have a line that's perpendicular to another line, how are their slopes related? Well, if you have a line that's perpendicular to another line, the slope of the perpendicular line is the opposite reciprocal, meaning the sign is different and you take the reciprocal. Well, the slope of my green line was 8, so take the reciprocal of that, you have 1/8, and then the opposite, and you have negative 1/8. So now we can write the equation of our line. I'm going to just write here that the slope for line 3, m, is equal to the opposite reciprocal, which is going to be negative 1/8. Okay, so now if I write this out, I have y minus 16 is equal to negative 1/8 times x minus 4. Okay, I can simplify this a little bit by multiplying this 1/8 times x and by negative 4, and then adding 16 to both sides. So what will I get? Well, I will have negative 1/8 times x, which is just negative x over 8. And then 1/8 times 4, well, it's going to be negative times negative, which will make it positive. And then 1/8 times 4 will give me 4/8, which is 1/2. And then I'm going to add 16 to both sides. So I'm going to have 16 plus 1/2, or 16.5. Positive plus 16.5. And that is the equation of the purple line. Okay, so now it's time to tell ourselves what the names of these lines are. So the red line is what's called the secant line. And a secant line is just a line through any 2 points. Okay, so the secant line, very, very simple, resembles the average rate of change, right? Line 2 is what we call a tangent line. And a tangent line to a curve, and so our curve here would be d of t, a tangent line is a line that passes through the same point. So you might say the line tangent to d of t at t equals 4. And that line is going to pass through that point and have the same slope as the curve at that point. And so line 2 is tangent because it passes through that point when t is 4 and has the same slope as our curve d of t at t equals 4. Line 3 is what we call the normal line, and it's normal is another word for perpendicular. It has the opposite and reciprocal slope of the tangent line. Okay? Passes through the same point but has the opposite reciprocal slope. Okay? So let's go ahead and define these more rigorously. Hopefully this example helped to kind of make what we're about to see in the definition make a little more sense. All right, here are the definitions now. So the secant, tangent, and normal to a curve, these are all lines. What I want you to be very aware of is that sometimes a question won't specify find the secant line or the tangent line. They'll just say find the secant to a curve or the tangent to a curve at some point or the normal to a curve at some point. And what you need to remember is that what they're specifying, what they're asking for, is the equation for that line. Okay? So for each one of these, there's kind of a sort of set couple of things that you're looking for that you need to be told in order to figure out what the equation is. And we'll talk about them. So let's start with the secant to a curve. That's a line through 2 points on a curve is a secant to the curve. And so if you're finding a secant line, what you'll need to be given are the 2 points through which that line needs to pass. Okay, so that's an important thing to remember. You'll need to be told what those 2 points that they want that line to pass through are. Tangent to a curve. So the line tangent to a curve, f of x, at a point a comma f of a. And I want to talk about what this means. So if you're asked for the tangent line, you'll have to be given the function, which the line is tangent to, and the point at which the line is tangent. So that point, your x value is a, and the y value is just the value of the function defined at that x value. Okay? And remember, that's because, as we saw in our example, the tangent line intersects the curve at this point. So they're going to touch each other at this exact point. And then the slope is going to be the same as the curve at that point as well. So let's read through this again. The line tangent to a curve, f of x, at a point a comma f of a is a line that goes through the point a comma f of a, so it intersects that point, and has a slope m given by m is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. And all that is, this slope is just the slope of the curve at that point A, right? So a tangent to a curve has the same slope as the curve at that point, okay? Now that's an important thing to remember. So for the tangent to a curve, you'll need to be given the point that it must pass through, okay? Maybe they'll just tell you the x value, and then you can find the y value by using the function. And that line has to have the same slope as the function does at that point A. And the way that you find that is using the limit as h approaches 0 of f of a plus h minus f of a over h. Okay? The normal to a curve is very, very simple. It's just an extension of the tangent. And the way that we define it is the normal line to a curve at a point is the line perpendicular to the tangent at that point. Okay, so what that means is if the slope of the curve slash the tangent, because the tangent and the curve will have the same slope, is m, then the slope of the normal is negative 1 over m, right? Opposite reciprocal. So the normal to a curve is just the tangent to the curve except perpendicular, meaning that its slope will be the opposite reciprocal. Okay? So if necessary, go ahead and maybe read through these once more, and then what I'm going to do is I'm going to draw a quick little diagram to help you visualize and hopefully never forget the definition of the secant, tangent, and normal lines. Okay, so here is the beginning of the diagram, and the reason I haven't done it all at once is I want to build on it so that you can sort of understand how the secant line kind of leads us to the tangent line. It's really a pretty simple process. So if I have some curve here, f of x, and then I've just graphed any general curve, and let's say that eventually we're going to get to the tangent of the curve at this point a comma f of a, right? So the x value is a, the y value is just the y value of the curve for that given x value, so it's f of a. And we can find the secant to the curve between this point and some other point off to the right. We'll just say that that point occurs a little past a, or a plus h. And the reason I'm adding this plus h here is so we can think about what eventually becomes the tangent to the curve. So the secant to the curve is just going to be the line that goes through any 2 points on the curve, and we'll just say that the first line is where you have an x value of a, and then, the first point is where you have an x value of a, and that second point is someplace off to the right. Okay, so I'll just quickly add in now that line. Okay, now we have the tangent to the curve. And what I want you to hopefully see is how the secant leads to the tangent. And so if you notice, the secant line has a slope that's dictated by the point a comma f of a, and then the point a plus h comma f of a plus h. And so what we're really doing when we're finding the slope of the line right at this point A is we're taking the limit of the secant line, the slope of the secant line, as h gets closer and closer to 0. Because what that's doing is that it's bringing that point to the right, down, 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 until we just basically are touching, right? And we're taking the limit of that slope, and so that's allowing us to find the slope right at A. Okay, so the tangent line to the curve at A is going to have the slope of this line right at A, the slope of the curve right at A, and it's going to go through this point A comma f of A. Okay, so there I've drawn it, and I've also written down the slope of each of the lines. So the slope of the secant line is just the way that we normally would calculate the slope of any line through 2 points, right? We have the point further to the right, the y value, minus the y value of the point further to the left. That gives us the change in y, and then the change in x is just the difference between the x values. And in this case, the difference between an x value of a and a plus h is just whatever you've added on, or h. The slope of the tangent I get by taking the limit of the slope of the secant lines as h approaches 0. In other words, bringing this other point all the way down and taking the limit so that I'm getting the exact slope right at A. So that's the relationship between the two. Then, of course, we have the normal line, and the normal line is really simple. It's just a line that's perpendicular to the tangent line and also goes through this point A comma f of A. Alright, so there's the slope of the normal line, which is just going to be the opposite reciprocal of whatever the slope of the tangent is. And you can see that it also passes through that point A comma f of A. So it might actually, I'm going to go ahead and make sure we label that point here. This point that it all passes through is the point A comma f of A. Okay, and of course you can write the point slope form for any one of these lines, right? It's going to be y minus, and the y value of a point that all of these lines passes through is f of A equals the slope, whatever the slope of your line is. And so in the slope of the secant, this is how you'd get it. The slope of the tangent is here, and the slope of the normal is -1 over m. So I'm just going to write slope so that you don't confuse it with any one of those. Slope, whatever the slope is, times x minus a, because that's the x value of the point that we're all going through. Okay? So the real key is to find the slope, and for this, the secant, the tangent, and the normal, the slopes are related but slightly different. Okay? So now let's go ahead and get a little bit of practice by finding the secant, tangent, and normal to a curve for a bunch of different curves. Alright, let's go through an example here for the function f of x equals 4 minus x squared. Find the secant between x equals 1 and x equals 2. Find the tangent of the curve f at x equals 1, and then we're going to find the normal. So I encourage you to first do this on your own. Obviously, if you can do it on your own, there's no need for me to help you go through it, and it will make you better at it as well. So go through it first yourself, and if you need any hints or help along the way, you can go ahead and press play for my work for the problem. Okay, for the secant line, basically we're finding the average rate of change between x values of 1 and 2. That's going to be our slope. And so an f of 2 is 0, f of 1 is 3, so we have 0 minus 3, which is -3 over 1, -3, and a point that it goes through. Looking forward, we know that we're finding the tangent and the normal at x equals 1, so it might just be helpful to find the point on our function, on our curve f, when x equals 1. So I plug in 1, I get 4 minus 1, which is 3, so there's my point. And so now I can write the equation here. Y minus 3 is equal to -3 times x minus 1. And I can go ahead and write this in slightly easier to work with fashion, solving for y, and I get y equals -3x. -3 times -1 is +3, and I'm going to be adding 3, so +6. tangent to the curve, I know that I need, again, the slope and the point to write my equation. Now, the slope of the tangent is the same as the slope of the function f at that point x equals 1. And so really what I'm doing is I'm going back to the definition, making sure that I'm remembering what tangent, the tangent to the curve is, and then I'm going out and I'm finding those pieces that I need to write that equation. So to write an equation for a line, I need the slope and I need a point. And so finding the slope of the tangent means finding the slope of the function. So I'm going to write slope of f at x equals 1, right? In other words, using f of 1. And so there I'm going to be using my definition for the instantaneous rate of change, or the slope of the curve, when the function, when the x value is equal to 1. And so here the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. Okay? So now I've got to plug into my function and continue solving. Limit as h approaches 0. 1 plus h, so it's going to be 4 minus 1 plus h squared. Okay, and then f of 1 is 3, so minus 3 divided by h. Now, here I can try substitution, but if I try that, notice that I'll get 0 over 0. So I need to continue working. I'll come over here. I'm going to go ahead and square that first piece out. So I'm going to have the limit as h approaches 0. Here I'm going to have 4 minus whatever I get from 1 plus h squared, which is going to be 1 plus 2h plus h squared minus 3 divided by h. Okay? And I can already see how this is going to help me out. 4 minus 3 is going to be 1. So let's just go ahead and make that change now. 4 minus 3 is 1. And notice that when I distribute this negative in here, I'm going to get a negative 1. So I'm going to be left with negative 2h minus h squared over h. And so now I can factor out my h. So I have the limit as h approaches 0 of h times negative 2 minus h divided by h. H over h is 1. Since I'm taking the limit, it doesn't matter that it's 0 over 0 when h is 0. And so now I just have to plug in 0, and I'm going to get negative 2 minus 0, or in other words, a slope of negative 2. So the slope is negative 2. Again, it goes through the point 1, 3. So I have my equation as y minus 3 equals negative 2 times x minus 1. And I, of course, can write this as y equals negative 2x. Negative 2 times negative 1 is positive 2 plus 3 plus 5. And this makes finding the curve, or the normal curve, very, very simple. Because if I go back to point-slope form, I have a point already, and the slope for my normal curve is the opposite reciprocal of what the slope of the function or the tangent line is at x equals 1. So the slope for my normal curve is going to be the opposite reciprocal, or in this case, positive 1/2. And so now I can just use my point-slope form, and I'll just come over here, and I will have y minus 3 equals 1/2 times x minus 1, and I can solve for y again here. I'll have y equals 1/2 x. Now 1/2 times negative 1 is negative 1/2, and I'm adding 3, so if I add 3 to negative 1/2, I'll have positive 2.5, or 2.5. Okay? So there's the equation of my normal line here's the equation for my tangent line, and here's the equation for my secant line. Alright, I will go ahead and give you now some to practice. Make sure that you're pushing yourself to get the correct answer and work all the way through, if for nothing else, so that you can present them to your classmates without being embarrassed. Alright, note that these are questions 9 through 12 on page 84, so you can check your answers here. And you'll also notice, if you're looking in your book, that I've written some of the curves as y equals, and some as in function notation as f of x equals, just so that you're always getting a different look, because it's really interchangeable, right, the way that they'll be written, and so you want to just make sure you're comfortable with no matter how they look. Alright, here are a couple more for you to take a look at. Notice again, one from the book, so you can check your answer and ensure that your answer is correct.